Okay, let's have a look at question 3, which looks to be about capacitors. So a physics student wishes to construct a capacitor which will store 31 nanocoulombs of charge when connected to an 8-volt power supply. Carries out some calculations and determines that placing 2 square aluminium plates side length 21 centimeters, a distance of 0.1 millimeters apart, as shown, will be suitable. And here's the diagram. Determine whether or not this capacitor setup will store the required charge. So determine typically means apply some physics, do some maths, and find out. There's 3 marks for this, and there's kind of 2 stages to this, because what we need to think about, we require this to store 31 nanocoulombs of charge. 31 times 10 to the minus 9 coulombs when 8 volts are applied, and we know that Q is equal to CV, so capacitance required for that to be true will be equal to Q over V. They couldn't have made it 32, had to be 31. So that is, can a person do that in their head? I'm sure you could if you tried hard enough, but I've got a calculator. Yeah, I kind of knew it. 3.875 times 10 to the minus 9. Farads is the unit. So that's the capacitance required. That's kind of the first step. The second step is to calculate whether or not this capacitor does have enough capacitance for that. So we need to use this formula that links the area of the plates, the permittivity of free space, and the distance between the plates. So we'll work out the capacitance. This is required. The capacitance of this actual setup then, area, just, take care with the units. It's 21 centimeters, and it's square, so 0.21 squared. Epsilon naught is 8.85 times 10 to the minus 12. And we're dividing that again, careful with the units. This is in millimeters, so 0.1 times 10 to the minus 3. Chuck that all into the calculator. And 3.9 times 10 to the minus 9. And yeah, therefore it is enough. This was our minimum requirement. So yes, determine whether or not this capacitor setup will store the required charge. Okay, part 2. State how the student could increase the charge stored without changing any of the dimensions or the power supply. So state, no calculations required is the implication of the word state. Yeah, so this is our setup, and it very clearly says without changing any of the dimensions. I would take that to mean we cannot change the area, we cannot change the distance between the plates. It also says we can't change the power supply. So how do we, if you look at the equation that we've used previously, we've used this and we've used this. V we're not allowed to change. We wish to increase Q without changing V, so we need to increase C. We're not allowed to change A. We're not allowed to change D. The only thing left to change is the permittivity. So how do we do that? We introduce a dielectric between the plates. And remember that a dielectric is just any material that is necessarily an insulator that's going to have a higher permittivity than the permittivity of free space. I imagine that's it. If this is a 1 mark question, I imagine simply saying add a dielectric between the plates is enough. But just for clarity, I'm going to say with higher permittivity. Than epsilon naught. I very much doubt that that statement is required. Part B. Combinations of capacitors C1, 2 and 3 connected to a 6-volt power supply. Determine the charges on each of the capacitors and the potential differences across them. 6 marks for this. So no sort of, this hasn't been separated up into parts at all. We're simply trying to find for each capacitor the charge and PD. So yeah, the way to go about this, there's a couple of key things to remember. If capacitors are in series, they must carry the same amount of charge, because if I think about current flowing around this circuit, whatever current flows through here, half is going to go through each of these and all is going to go through this one. The reason I say half is because these two capacitors are the same size. So that's the first thing to bear in mind. Other things to bear in mind, you know, this is basically application of Kirchhoff's laws. The PDs across C1 and 2 will be equal, and whatever PD that is across this parallel section added to the PD across C3 must equal 6. So those are the types of rules that we're going to use. For me, the lead into this question, the first thing I would do would be to calculate the total capacitance and therefore calculate the total amount of charge that is going to be stored by this whole setup. So if I do that, yeah, I've got C1 and C2 are in parallel. So their combined capacitance C1, 2 is just the sum of the two. Remember, capacitors are kind of the other way around to resistors. You add them when they're in parallel, and you add the reciprocals to get the reciprocal of the total when they're in series. So combined C1, 2 is 4 microfarads. And then C1, 2 is in series with C3. So when we combine those, the total capacitance, the total capacitance is given by adding the reciprocals. So 1 over the total capacitance, 1 over C1, 2 plus 1 over C3. So what have we got here? 1 over it plus 1 over 4. Gives me it over 3 microfarads. So that's the total capacitance in this circuit. Therefore, the total charge is given by that. That needs to be equal to it over 3 times 10 to the minus 6 multiplied by 6 equals 16 times 10 to the minus 6 coulombs. So going back to what I was saying about this is the total charge stored. So, you know, we talk about capacitors storing charge, but really what we mean by that is it's the amount of charge that appears to flow through them. If 16 times 10 to the minus 6, 16 microcoulombs of charge have appeared to flow through this cell, then 16 microcoulombs of charge have flowed through C3. So C3 is where we'll start. So the charge on C3 must be equal to that. (16 microcoulombs). So remember, if I have any circuit where capacitors are in series, the total charge has to appear to flow through both or all of them. So that's my charge on C3, and since I can use Q equals CV for that capacitor on its own, I can say that the potential difference across capacitor 3 then is just equal to the charge on it divided by that capacitance, which is equal to 16 times 10 to the minus 6. Capacitance is 8 microfarads. Which is 2 volts. Straight away, that tells me the potential difference across C1 and 2. They're in parallel, they must have the same PD across each, and we know that the PD here is 2 volts. I've got 6 volts total, so I know that the PD across C1 and C2 must be 4 volts. That, I could write that and use that to calculate the charges on capacitors 1 and 2. Alternatively, I could say that this total charge, where is it? This total charge, because these two capacitors are in parallel and they're equal in size, that charge is shared evenly between the two. So the total charge that flows through these two by Kirchhoff's first law about current, if you think about the total amount of current flowing here, must equal the sum of the currents here and here, and that recombines over here. So whatever charge in some amount of time has flowed through C3, it must be equal to the sum of the charge that's flowed through C1 and C2. And since they're equal in capacitance, they will split that total charge evenly between them. So C1 and 2 in parallel and equal in size. So they share QT evenly, which implies that the charge on capacitor 1 equals the charge on capacitor 2 and is equal to 16 times 10 to the minus 6 coulombs over 2, which is 8 microcoulombs. And then I can use the equation that I've used here. Q1 equals C1 V1 implies V1 is equal to Q1 over C1, which is 8 microcoulombs, 8 times 10 to the minus 6, divided by 2 microfarads. Which gives me the 4 volts I was expecting, because the alternative method I could have used here would be to simply say that by Kirchhoff's second law, the PDs must sum 6. So if C3 has 2 volts across it, that parallel segment must have 4 volts. So that's V1 and C2 in parallel. So V2 equals V1 equals 4 volts. Is that everything I've been asked to do? I think it is. Determine the charges on each and the potential differences across them. I've got the charge on C3. I've got the PD across C3. I've got the charge on Q1 and C1 and C2, and I've got the PDs across them. So I think that's everything for 6 marks. Part C, the final part to this question. Two identical capacitors A and B are charged to a potential difference V. Capacitor A connected to a resistor of value R. Capacitor B is connected to a resistor of value R over 2. The time taken for the charge on A to decrease from 16 to it is given by T. So 16 to it, that is a single half-life, if you like. The time taken for the charge on capacitor B to decrease from 16 to 2 is given by capital T. This time we're halving 3 times from 16 to it to 4 to 2. Show that T is equal to 3T over, show that T, capital T, is equal to 3 times lowercase t divided by 2. Okay, it's a slightly bizarre setup, this one, I feel. So I think the way I would start this, in general, T half for any capacitor is equal to RC times natural log of 2. That would be my starting point. So therefore, 16 to it is 1 half time. So therefore, I can write that TA, the half time for A, is equal to lowercase t, and that is given by RC natural log 2. A is connected to just R. That's fine. TB on the other hand, T half, the half time for B. Oh my goodness, I'm running out of subscripts here. The half time for circuit B using capacitor B, it's connected to R over 2, so it must be equal to, because it's connected to a resistance of R over 2, and that is equal to T over 2, therefore. And it drops from 16 to 2, implies that is 3 half-lives. Which is therefore equal to 3T over 2. Therefore T is 3T over 2. Yeah, so not that bad really, just a slightly unusual question, I feel. That's it.